So this tutorial is on error estimation and adaptive refinement. The usual adaptive loop that's sacrosanct is solve, estimate, mark, refine, and repeat. Okay, so we are going to see implementations of each of these steps in this tutorial. Here's a geometry that I'm told is from the early days of Netgen, 20-something years ago. Without going into the details of the construction of the geometry, this is supposed to be a chip that is getting heated up for various reasons. And I think I wanted to ask Joachim, he's not here. I think Joachim had once told me that it's a Soviet chip. Okay, so here is a problem to solve with a coefficient lambda in front of the div grad operator or the describe grad form, and this lambda has discontinuities. In this, there's one value here and another value outside and so forth. And we expect the solution, therefore, to have singularities because of these changing material properties. We make the Lagrange finite element space before we start doing the adaptivity, and here is the coefficient function. You see that there's a very large value on one of the subdomains. And we make a heat source, a uniform heat source in this region called the chip, the one in the middle. And we want to solve the Laplace problem with this varying material coefficients. Okay, so first we write a routine that updates the finite element, the grid function, and assembles the bilinear form, and just use the conjugate gradient method for solving the system. So we compile all these steps into this one routine so that we can keep calling this routine over and over again. We solve it once. On this coarse mesh, you see that there is the heat entering through the chip and then dissipating outside. Okay, if we want to capture a nice solution, then we have to refine the mesh in some places, and for that we need an estimator or an error estimator. And the estimator that's implemented here is a famous gradient recovery type error estimator, goes by the name of Sienkiewicz-Zhu, and we do the implementation uses an HDiv finite element space and a grid function from the HDiv finite element space. HDiv finite element space is a vector value finite element space with normal continuity. When we take the Lagrange finite element space and we take the gradient of the Lagrange finite element solution, we get a discontinuous vector field. We've seen that in one of the previous tutorials, and we're multiplying by the material coefficient, we get an approximation to the flux. That's a discontinuous approximation. We then set it into the HDiv space to make it normal, and to have it to get a function which is a flux approximation with normal continuity. And then, so that's this function. This is what we just made, IH of lambda grad UH. And we look at the difference between this interpolant, this HDiv interpolant, and the flux that is computed from the Lagrange finite element. That difference is a measure of error. When that measure of error is large in some areas of the domain, we have to refine those areas more. So that's how we create an error estimator. So implementation of this eta. You can recognize the components here. This is flux minus the interpolant. This is the flux, and this is the interpolant in the HDiv space. Take the difference of it, square, and multiply by 1 over lambda. If you plot the error representation, you see that here is a region where you would need to refine in order to capture the error better. Okay, so this integrate function we've seen before in the tutorial before, but without this argument. This argument is interesting for error estimation techniques. It says that instead of integrating over the whole mesh and giving you a number, integrate over each element and give me numbers corresponding to to the integral value on each element. So it's going to return a list where each value corresponds to the integral over a single element. Okay, and these are the values. So these are the estimates for the error in each element. So one value per element, and it leads us to identify elements which can possibly have large errors. And so we use this estimator for deciding which elements to mark for refinement. Here is the marking procedure. You run a loop over all elements and set a refinement flag if the estimator on that element is greater than a certain value that you prescribe. So here it's a quarter of the maximal error value. You can tweak these numbers to get more aggressive refinement or less aggressive refinement. Okay, and then there's a loop over, there's a Python loop here which can be replaced by vectorized alternative. We'll talk about that later. But let's do the entire adaptivity loop first. So we solved, we estimated the error. Now we just marked the elements with high error, and now we're going to refine those elements and then solve again. So now you see what happened. There's more elements here, and you solve the problem again. And if we keep doing this, it'll put more elements in the places where the error is large. And now let's automate the procedure. Here's a calc error function, which has the components of the steps that we discussed individually. It's all put together inside this one function. And using this calc error, we can run the adaptive loop. We solve, increase the refinement level. It's not a uniform refinement, it's a local refinement. Using this calc error, we mark the places where we need to refine, and this should do the loop. As you can see, we're printing out some of the adaptive iterates. You see how at the corners where you expected singularities, it's picking up more and more mesh points. And the maximal error is going down. Every 5 iterations a picture is generated. Okay, now by 51,000 degrees of freedom, we have essentially converged to machine precision in terms of the error estimator, at least. Okay, and we can plot, I think we've saved the errors in each iteration, and we can plot it to see how the progression of errors as the mesh is locally refined automatically. So you see the errors decrease, and at the bottom are the number of degrees of freedom. Okay, questions? Peter.
This is trying to get normal continuity into the otherwise discontinuous gradient.
Yeah, it's an estimator that says if you make up an improved flux approximation, then look at the difference between the improved flux approximation and the original flux approximation. That should give a measure of error.
Okay, so it's just saying that's the error, and so we're trying. Ultimately, that is, I'm seeing this as like the formats, like except for right at the, the hard edges, it has essentially now almost like H2.
You mean at these points?
Yeah, not there, but like everywhere else, it's like almost has a smooth radial derivative, or smooth normal derivative.
Yeah, it's improving the solution, yeah.
So this is sort of like cheating to get into N2 almost, or H2.
No.
No.
We're still using Lagrange finite elements.
Oh yeah.
So.
And I also was noting
the solution is likely not in H2 because of nasty singularity there.
I guess I meant not at the boundaries though.
Ah, yeah, okay.
So when the mesh is refined, so what's kind of strategy? It's a kind of splitting elements or any other
Yeah, you want to. How is the mesh split? Bisection procedure? You want to say something about the bisection procedure? No.
Mesh splitting. Bisection. The splitting the element or
It's back to how's a subdivision? It's bisection.
So and once an element is marked for refinement, it's bisected, and at the edge that gives you improved quality, or the best quality possible, and then surrounding elements are refined in order to make it a conforming mesh. Just enough. You kind of see some of the bisections, like this was an original element, I think, and then this element got bisected like that.
In 3D it's an Arnold-Poincaré algorithm.
Other questions?
When you do the timing, so this Python marking loop was the slowest part of the whole loop before vectorization, before switching this marking to NumPy.
I see.
And it's a decision in Python was so slow.
Okay, yeah, I sort of ran over that. Here is the vectorized alternative of how you do without a Python loop. You could do. Okay, so
I just order one Python operation, and the decision is done from NumPy, and the output from NumPy is directly put into the netcat mesh.
This when I went over it earlier, this was a list. Now this list is a NumPy array, and this operation therefore is vectorized.
Yeah. Why are they talking with the refine?
So the elements 2D NumPy, this is also data for the 2D elements. So vertices, material properties, and one. So it's an array of structures. We say refine, we access the refinement bit of all elements at once. It's a NumPy array view of the.
That's a NumPy bit array.
Here, where I think Joachim is explaining what happens when you do this is changing this thing element by element. Each element 2D gets a refine equals true. This is
an array of 2D elements. NumPy is a number array of, how do you call them, user-defined structures.
Yeah.
So basically you can also export the C++ structs to be able to be used in NumPy, so you need to give all the offsets of data and so on. And then you can access them like that. So you can, for all elements in the NumPy array, you can access, I don't know, the element number or the element refinement flag or whatever.
Here's the data type. Yeah. It's a NumPy array of this particular made-up data type.
Quite recent feature.
Okay, if there are no questions, we'll proceed to the next one.